Hello, my name is Prathamesh and I am with my friend Arav here for our Data Structure Internet Assessment podcast. Our project addresses a common real world problem, the inefficiency of fixed time traffic lights. Our goal was to design an intelligent system that uses data structures to manage traffic dynamically. This system prioritizes the most congested lanes, but critically, it guarantees immediate access for emergency vehicles using a priority override mechanism.
Hello, my name is Arav and I would like to discuss about the data structure we used in the reason why we chose it. The entire system is built on the two core data structures. First, each traffic lane is a queue modeled by the traffic lane class. This is a simple first in first out structure. The first car in line is the first car in out. We implement this using standard queue, NQ and DQ logic. Second, the light's decision-making process functions as the priority queue. When it's time to change the light, the system doesn't cycle sequentially. Instead, it checks all the four lanes and always grants the green light with the highest calculated priority score.
The intelligence is all in the priority score logic, which is handled by the compute signal weight function. This function has two main rules. Rule A is the emergency override. If an ambulance is present, we instantly assign an overwhelming score of 1000. This ensures that no matter how many cars are in the other lanes, the ambulance always receives the green light immediately. Rule B handles normal congestion. Here the score is directly proportional to the vehicle count, allowing us to dynamically manage peak traffic flow.
Now let's look at the working simulation. This is built in a single C file translating our logic for a real life simulation. In our code, we can see the variables at the start that defines the urgency override score and other variables, after which we define our structures and functions. On line 40, we can see that the add vehicle function which adds the vehicle to the stack and immediately after the DQ function to remove it. This function will be used a lot to remove more vehicles. On line 80, we can see a function to assign priority weight according to the vehicle.
From line 108, we can finally see the function which decides and dequeues the lane with the highest priority. Line 154, we can see the conditions for what to dequeue, and it dequeues the entire lane if an ambulance is detected, else it dequeues 3 vehicles for that lane. Lanes are chosen on the basis of their weight which is assigned by the previous function. Finally, we can see the main function which gives instructions and simulates and outputs the code.
Scenario 1, congestion. We started with 8 cars in the east arm and only 2 in the south arm. As you can see, the light selects east, then west, and not an anti-clockwise cycle, reducing the heaviest congestion first. This proves the system is dynamic and not fixed.
Scenario 2. The emergency test. I will now show you an ambulance lane which has low traffic. Notice, the system prioritizes the ambulance lane in the next cycle. Switch the light to arm 2 and clear the ambulance. This demonstrates that a priority queue logic is functioning correctly by forcing the urgency override score to the top of the queue selection process, providing the life-saving capability of our design.
In conclusion, this project successfully models a smart traffic system using the queue structure for traffic lanes and the priority queue logic for dynamic signal switching. We achieved a fully functional simulation and importantly secured a 5% original score on Turn It In. This system is ready for the real world testing to reduce delays and save critical emergency responses time. Thank you.
Hello, I'm Bhargav from Group 5. I reviewed your traffic management code and found your C code to be very well structured. Yet, I have some few questions about the data structure implementation.
Thanks. I am Prathamesh from Group 16 and this is Arav. We are ready for your questions. We are proud of how we implemented the priority logic.
Yeah, so my first question was you implemented traffic lane T struct model using a standard C array, but C doesn't support dynamic resizing or queue methods. So how did you implement the first remove vehicle function so that it ensures the FIFO behavior?
That's the key question. We modeled the FIFO behavior by stimulating the action. When the light is green, the remove vehicle from arm function doesn't just decrement the count, it executes a shift operation. We loop through the array and physically shift every remaining element one index forward. This forces the entire queue to advance, ensuring that the vehicle at the front index IDX is conceptually removed and the second vehicle becomes the new front. This maintains the FIFO invariant despite the array being static.
Okay, so I have another question for you guys. So your core feature is emergency override. So how does the system technically guarantee that an ambulance is in a completely empty lane? Does it instantly win priority over a massively congested lane that might have much normal score? What's the scientific mechanism that you've used in the compute signal weight function?
Sahil, we solved that by using a static prioritization constant in the compute signal weight function. If the ambulance is present flag is true, we immediately assign the lane a very huge value. The urgency override score is 1000. For comparison, the standard traffic is scored at 10 points per car. If another lane had maximum 50 cars, its score would be only 500. By assessing 1000, we ensure that the ambulance score is mathematically guaranteed to the maximum and thus the absolute winning arm during the priority queue selection loop. We prioritize the ambulance through this.
Okay, I seem satisfied with your answer.
Oh, okay, I have one more question. If this, if your code were to be scaled for a large city where there are like tens of thousands of vehicles moving, how will you change the code, or which data structure would you use to improve the performance of your code?
Our current implementation, while clear, is indeed a limitation for scalability. The shift operation means that dequeuing a single car requires moving every other car behind it, giving it a time complexity of O(n), which is inefficient when n is large. To scale to scale this, we would immediately switch to a circular buffer or a linked list. Both allow us to adjust the pointer in O1 time, meaning the removal operation would be constant regardless of the queue size, making it suitable for citywide simulation.
Okay, so that answers a lot of our questions and addresses the essence and the core complexity of our topic. Thank you so much for your time, guys.
Thank you for your excellent questions.